Hazel. Birthday Hazel. Come here, Hazel. 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 Come here. Whoa. All right, hello class. I'm here with Hazel. Hope you guys are doing well.
Ooh, that was nice, Hazel. Thank you.
So I am happy to report that Mr. Bugs is feeling better. So he stopped whimpering. Wow, Hazel. And he's outside playing right now. So one thing I want to reiterate is that if you guys are feeling like the work that I'm assigning is too much, just don't do it all. Do the amount of work that is appropriate for you, given what you're going through. All right? Oh, Hazel, you're so sweet. Oh, you vibrate your face. Why you vibrate your face again? Why you vibrate your face again? Why don't you look at the camera? There's a camera right here. Why don't you look at it? Okay. So I've got another paper 2 for you. And I'm going to do 3, I believe it's 3 of the problems I'm going to do today. And then you guys are going to do 2 problems. So let's get started. The first problem is number 3 that I wanted to do is number 3. It says, shows this like it's going to be a Snell's law problem because we can see there's an angle of incidence and there's a boundary between materials. So this is a wave that's refracting as it exits the metal sheet. A particle P in the metal sheet performs simple harmonic motions. When the displacement of P is 3.2 micrometers, that's what that U means, the magnitude of its acceleration is 7.9 meters per second. Calculate the magnitude of the acceleration when P is at a displacement of 2.3 micrometers. Okay, so we're doing question. This is part A. So one of the things about simple harmonic motion, which I call SHM, SHM has to do with the elastic force. So when something is undergoing simple harmonic motion, it is the elastic force that is acting on it. Okay, so if we write Newton's second law, net force equals ma, we can see the force is the elastic force, which is minus kx. So minus kx equals ma. All right, so the first sentence of this, the second sentence says that when the displacement is 3.2 micrometers, so x is equal to 3.2 micrometers, the acceleration is 7.9 meters per second squared. Okay? Then for the next part, it says when the displacement is 2.3 micrometers, what is the acceleration? Okay, so I don't know the mass of the particle. But you'll notice that if I take the ratio of these equations, then the k's cancel out and the masses cancel out. Okay? And so what I get is 3.2 over 2.3 equals 7.9 over the acceleration. And so that's going to allow me to solve for the acceleration. 3.2 2.3. Hey, Galen. Part B. The wave is incident at point Q on a metal-air boundary. The wave makes an angle of 54 degrees with the normal. The speed of sound in metal is 6,010 meters per second, and the speed in air is 340 meters per second. Calculate the angle between the normal at Q and the direction of the wave in air. So this is just a straight up Snell's law problem. N sine, so N1 sine of theta 1 equals N2 sine of theta 2. Now, one thing I want to say is we learned Snell's law in the context of electromagnetic waves. It applies to all waves, okay? So you might remember that the index of refraction is defined as C over V. So I have C over V1 sine of theta 1 equals C over V2 sine of theta 2. So notice how the C's cancel out. Okay. So I'll go ahead and the following. So we have 1 over 6,010 sine of 50. Going to have to do an arc sine, inverse sine. And I get 2.6 degrees. All right, it's windy here. C, I. It says state. Well, okay, so it says the frequency of the sound wave in the metal is 250 hertz. State the frequency of the wave in air. Whenever it says state, it's giving you a hint that the answer is really simple. Okay, it doesn't say calculate, it doesn't say reason, it just says give us the fact. Okay? And one of the things I taught you is that the frequency of a wave does not depend on the medium as it travels. Okay, so as a wave is traveling, its frequency remains the same. So it's going to be 250 hertz still. Determine the wavelength in air. Wavelength is V over F from the fundamental wave equation. In air, the speed of sound is 340, and the frequency is 250 hertz. So that would be 1.36 meters. All right. Part D, the sound wave in air in part C enters a pipe that is open at both ends. The diagram shows the displacement at a particular time t of a standing wave that is set up in the pipe. On the diagram at time t, label with the letter C a point in the pipe that is the center of a compression. Okay, so a compression is a point where the displacement This one's going to be a little bit tricky. If we look at it, if we look at a particular point here in the medium, if it's a compression, then the points to the right of that point get displaced to the left, and the points to the left of that point get displaced to the right. Okay? And because that would have the effect of squishing from both sides. Okay? So if I look at this, this is a graph of displacement, and I can see that this point right here, if we look at the points to the right of it, over here, for example, see how the displacement is to the left. So the points, see how the graph is negative here, which means displacement to the left. So that means that the point that I drew a dot on, that is the place where it's a compression. And you can see that the points to the left are displaced to the right. So that spot is going to get squeezed. All right. Oh, man. I thought they were going to start to ask me about open instruments, and they didn't. That's a bummer. All right. The next question I'm going to do is question 4. Hey, Charlie. Hey, Charlie, I'm not getting your homework responses. All right, so number 4 is a circuit problem, it looks like. 3 identical bulbs, X, Y, and Z, each of resistance 4 ohms, are connected to a cell of EMF 12 volts. The cell has negligible internal resistance. The switch is initially open. Calculate the power dissipated in the circuit. So one of the things we can see is that if this switch is open, then no current can flow through this top branch of like that. In that case, it would be 8 ohms because you have the Y and the Z in series with each other. And then you have I equals V over R, which equals 12 over 8. So that would be 1.5 ohms in that case. B says the switch is now closed. State without calculation why the current in the cell will increase. Well, basically, if we close the circuit so that now this is allowing current to flow, you've added another pathway for the current to flow. Now the current can flow this way, whereas it wasn't able to go that way before. And so that means that the resistance in the circuit went down. In fact, you could calculate, if you wanted to, that the total resistance would now be 8 ohms in parallel with 4 ohms. So that would basically be Y plus Z in parallel with X. Okay, which is going to be less than 8 ohms. So basically the resistance went down, so the current went up. Oh, you know what? I forgot to even answer A directly. This should be 1.5 amps, by the way. And then power equals I times V would equal 12 times 1.5 equals 18 watts. Okay. Deduce the ratio. So that was BI. Now I'm going to do BII. Deduce the ratio of the power dissipated in Y when S is open to the power dissipated when S is closed. So as I said, when S is closed, the switch is closed, we're going to have this resistance. Okay? So when the switch is closed, the resistance is 8 in parallel with 4. Which is 2.7 ohms. Okay. So that means that my power when the switch is closed is going to be V squared over R. It'll be 12 squared over 2.7 equals 54 watts. So the power when the switch is open to the power when the switch is closed is 18 over 54. And I'm going to do one more question for you guys, which is number 7. So let me scroll to number 7. Ooh, number 7 is mercifully short. Number 7 says determine the average ocean surface temperature is 289 Kelvin. Oceans behave as black bodies. Show that the intensity radiated by the ocean is about 400 watts per meter squared. So if we look at the Stefan-Boltzmann Law, so this is a climate change problem. The Stefan-Boltzmann Law says that P equals epsilon sigma A T to the 4th. Okay? Now notice how it says the intensity radiated by the ocean is watts per meter squared. Watts is a unit of power. Per meter squared, that's a unit of area. So notice how it didn't give us the area of the ocean, but it's asking us what is the watts per meter squared. So it's actually asking us, the question is asking what is the power per area. So that would be epsilon sigma T to the 4th. And then it says that the ocean behaves as a black body. And we know that perfect black bodies, I can make it a heart. A perfect black body has an emissivity of 1. Sigma is the Stefan-Boltzmann law, 5.67 times 10 to the minus 8. And the temperature, it tells us, is 289. So let me type in those numbers. And I get 396 watts per meter squared. So that's close to 400. Part B. Explain why some of this radiation is returned to the oceans from the atmosphere. Okay. So basically, the atmosphere is not perfectly transparent. Okay. So if we think about this as the ocean, and we think about this as the atmosphere, and here's the surface of the water, some of the light or some of the radiation that comes out of the atmosphere is actually going to get reflected. It might get reflected off a cloud. It might get reflected off of particles. And it's going to get reflected back down to the surface. Okay? So that's one thing that can happen is reflection. Another thing is some of the radiation that leaves the ocean could be used to heat up the atmosphere. So now the atmosphere is hotter. And if the atmosphere is hotter, then that means it emits its own radiation, Now, the atmosphere has an area that's open to space, so it's going to emit some of this there. All right? So, for your daily items, you are going to work out questions 5 and 6 from this paper 2. And I hope you guys have a good day. I've been playing this board game. It's called Dominion. And if you haven't played it before, I would check it out. It's really fun. Good way to pass the time. All right. I will see you tomorrow.